I'm going to be giving you a little bit of an introduction to some of the work that we've been doing in Liverpool for the last couple of decades, actually, on trying to understand a little bit more about how the universe works, and in particular how it changes. And I'm going to be talking quite a lot about this beautiful thing here, which is my giant telescope that I play with, but I'll be explaining why we built it, what we're doing with it, and what we're going to do next, because you've always got to keep looking to the future. But I want to start by just telling you what physics is, which may seem a bit weird at an Institute of Physics talk, but it does mean quite different things to different people. To me, new physics is about pushing. It's about going to the fundamentals. It's about finding the extremes that you haven't been able to study before. And you can do this in lots of ways. You can build giant experiments like the Large Hadron Collider. Cameras there bigger than this hall. You can study it in tiny little detail by exploring through chemistry. You can even do physics by exploring through biology. But I do it by looking at the universe, because the universe is a very extreme place. It's full of stuff that we can't reproduce on the Earth. Black holes, neutron stars, supernovae. This picture in the background is the remnant of a star that exploded, a supernova remnant. So this is the shock wave from the debris of the explosion. And that's pretty extreme itself. Supernova in about an hour lets out more energy than the sun will do in 10 billion years. So they're incredibly energetic. But the most extreme thing you can't even see, because it's left in the middle. It's what's left of the core of the star that exploded. And the core of the star gets crushed down by the explosion and by gravity until it becomes incredibly dense. In this case, it's a neutron star. And neutron stars are ridiculous. Other than black holes, they're pretty much the densest things we know of. They're actually slightly denser than the nucleus of an atom. If you were to take a piece of neutron star about the same size as my laser pointer here, that would weigh as much as Wales. And I mean the country, not the animal. Just try and get your heads around that for a second. I mean, we hear these analogies all the time, but try and actually imagine that. Getting all of Wales, all of the mountains, all of the buildings, all of the people, all of the sheep, all squeezed down into this. That's incredibly dense. Now, we can't reproduce that on the Earth. Maybe for a tiny fraction of a second, but not enough to really study it in detail. So if we want to understand really dense things, we have to look at the universe. And so that is what astronomy is, and astrophysics. It's doing physics where the universe is your laboratory. Using the extremes and the fundamentals that are already out there to try and understand a little bit more about the fundamental laws of nature. So we don't study stars just because we like stars, although we do. We study stars because they might tell us something fundamental about atoms, or quarks, or nuclear physics. So we're always looking for unusual and different ways to study the universe, because then we can find extremes and fundamental things that we haven't spotted before. And that's a challenge, because the sky is really difficult to see. This is what I see if I go out roughly where I live. I'm actually quite lucky, I live on the coast. But if I go a little bit further inland, and I go out on a clear night, I see orange, with a few dots. I suspect the skies around here are a little bit better than the skies I have next to Liverpool. But nevertheless, basically what you see with your eye is orange from the streetlights and a few dots. You get away from the streetlights, you see more. You see a few more stars. You see the glowing band in the Milky Way. Just a show of hands, who here has actually seen the Milky Way? Not the chocolate bar. Oh, this is fantastic. Thank you. It's awesome, isn't it? Just seeing that thing splashed in the sky above you. But you don't really see it properly. Looks like a cloud. Weird, slightly glowing cloud with splodges in it, but nevertheless a cloud. To see it properly, we can't just use our eyes. Our eyes are not very good for astronomy. That's not what our eyes are for. If you think about it, evolution designed our eyes to stop us getting eaten by saber-toothed tigers and stuff like that. It's not about observing the sky. So if we want to see what's really happening out in the universe, we have to use instruments, telescopes and cameras. They can do things that our eyes can't. One of the simplest things that a camera can do is just collect light for longer. Open the shutter, leave it open for a long time. This is a photograph taken of the night sky above the Palm, the Canary Islands. And it's about a half-hour exposure. This is actually quite an old one. This was taken on a film camera. Tells you how old it was, not digital at all. But you can see an awful lot more. You can see a lot more structure. You can see colours. You can see patterns. You can see a lot more stars. And until we can see it, we can't try and understand it. We don't answer the questions because we don't know what the questions are. So when you can see stuff like this, you see different coloured stars, you see big red fuzzy clouds, you see that the glowing down of the Milky Way doesn't look like a cloud anymore, it looks like what it really is, lots and lots of stars. Once you can see that, then you can try and understand them. And so in astronomy, we make progress in a slightly different way to all the other branches of physics, certainly physics, but probably all the other branches of science. We don't do it by experimentation. Most science is experimental. You build the experiment, you run the experiment, you look at the results. If you want to learn something new, you change the experiment. We can't do that with the universe. If I'm a chemist and I want to heat something up, put a Bunsen burner under it and it gets hotter. It's not complicated. We can't do that with bits of the universe. We can't get a giant Bunsen burner and put it under the sun to see what will happen. It's probably a good job actually, or some lunatic would do, but we can't do things like that. We can't change the universe. All we can do is see it. So we don't make progress by experimenting with the universe. We make progress by finding better ways to look at the universe. The picture on the right here is actually some of our students from Liverpool out in Tenerife as part of their degree. We take them out there for a week or two in the summer as in the second year of their degree, because until they've gone out to a telescope and they've pointed it at something and they've collected the data, they don't really know what astronomy is. They might know all the physics that they need to know, but they don't understand what you can and can't do with a telescope, what you can and can't do by observing. So when the students come back from their field trip, okay, they've had a great week on Tenerife, but the most important thing is they suddenly feel like they're really astronomers because they know what the limitations and advantages of observing are. It's an incredibly important part of their programme. So we've got quite good at looking at the universe. And we've been using telescopes for 400 years. We've been using cameras for best part, a bit over 100. We've got very good at collecting data. So there's a lot of things about the universe that we understand. But there are still some very important things that we don't understand. And I'm just going to show you a few fairly random examples of stuff where there are questions we haven't answered yet. This is an asteroid. Asteroid called 433 Eros, observed by a satellite. And basically, it looks like a rock. That's because it's a rock. They're not fundamentally exciting, but actually it's a very interesting rock. It's not an interesting rock because it's weird, it's an interesting rock because it's normal. And it's very, very old. The asteroids were made about the same time as the Earth was. They were made from basically the same stuff that the Earth was made of. But they haven't changed much since. They've just gone round and round in circles being rocks. The Earth has changed a lot. We've got volcanoes, we've got weather, we've got oceans, we've got life. All of these things change aspects of the Earth. And so if we really want to understand where the Earth came from, this is a good place to start. We study an asteroid, we're studying the history of the Earth. We can then look at those changes and try and understand them as well. So that's one reason why these asteroids are important to understand. There is another reason. Although it's a rock, it's quite a big rock, and it's moving very, very fast. And so if it hits us, we're going to die. This is a bad thing. And so finding these things before they hit us and doing something about it is something that astronomers need to do. I'll be coming back to that a little bit later. Another example of things we want to understand. Exoplanets. Extrasolar planets. Planets going around stars other than the Sun. Now, the particularly observant among you will have noticed that this is not an observation of an exoplanet. This is a drawing of what an exoplanet might look like. The reason I'm showing you an artist's impression is because all the pictures are rubbish. If you're really, really lucky, you can just about see a dot. Woo! But they're important dots, because they'll tell us something about the formation of planets, how common planets are, and they just might tell us something about life in the universe. But the reason we don't have these pictures, the reason that all we can see if we're really lucky is a dot, is planets are very small and they're very far away. So they're really hard to study. We can detect them, but studying them is another whole ballgame. And then there's this thing again, supernova. Supernova are awesome. Several of my colleagues at Liverpool spend their entire time finding and trying to understand supernovae. They're exploding stars, we understand that, but what we don't understand is the details of the explosion. And that's important because this explosion is driven by nuclear physics. It's driven by radioactive decay. And it's radioactive decay that we don't, of a form that we don't really get on the Earth. And it makes new atoms. Inside a star, like the Sun, bigger or smaller, doesn't matter, you've got nuclear fusion going on. You've got hydrogen being stuck together to make heavier elements and so on. And that works until you reach iron, and then it stops. If you want to stick iron together, you've got to give it energy. Lighter than iron, you stick them together, you release energy, but above iron, you've got to give it energy to stick them together. And so, there shouldn't be any elements heavier than iron. And we know there are, so they have to be made somewhere other than inside the normal processes of the star. And the best place is blowing the star up. Because suddenly you get a huge release of energy, you can smash those bits of iron together and they can stick together and make heavier and heavier elements. And so heavy elements are made inside these exploding stars. But the other important thing these explosions do is they spread the stuff around. You might be making nitrogen, carbon, oxygen inside a star, but if it stays there, you're never going to have us. There wouldn't be anything like enough of these elements in the universe. So the only way of getting it out of those stars, well, one of the only ways of getting it out of those stars, spreading it out into the universe, is to blow the stars up. And so we are made of the debris of these exploding stars. So it's important that we understand them. But we don't. We know the basics, we know roughly what's going on, but there are some very important details of the nuclear physics which we just don't get yet. So we need to study these in a lot more detail. And then there's my own personal favourite, supermassive black holes. Not just any old black hole, let's go for the really big ones. These things appear to be everywhere. This is one of the first supermassive black holes ever found. And you can't see it because it's black. But if you look at the movement of these stars, you see they're going in orbits. Now these are stars right in the centre of our own galaxy, right in the core of the Milky Way. And you can see this star in particular has done a beautiful orbit. Slightly tilted so it looks oval, but it's actually quite a good, fairly circular orbit. And because we understand orbits, we've understood orbits ever since Newton came up with the maths, we can work out what that star is orbiting around. We know it's underneath that little cross right in the middle of the picture. We know it's very, very massive. Maybe 10 million times the mass of the Sun. We know it's very small because the star didn't hit it. And we know it doesn't make any light. So it's incredibly massive, it's incredibly small, and it's black. It must be a black hole. If it's not a black hole, it has to be weirder than a black hole. So we found a supermassive black hole in the centre of our galaxy. Now that was exciting news about 20 years ago. But we've moved on since then. And we're finding these things everywhere we look. Any galaxy where we would expect to be able to find something like this, we always find it. We're always finding these supermassive black holes in the centres of galaxies. The bigger the galaxy, the bigger the supermassive black hole. 10 million solar masses, 100 million solar masses. But the real thing is, we don't know how you make them. We know how you make small black holes, 1, 2, 3 solar masses. And the only way we can think of to make really big ones is to keep throwing stuff into a black hole until it gets bigger. But we don't see the ones in the middle. We see 10, 20, 30 solar masses, and then we leap up to 10 million. Don't see the ones in between. So where are they? Does it happen so fast that we miss it? How can you make something that big that quickly? We don't understand. And so there's some very fundamental questions here we need to get to grips with. Now I chose these 4 random bits of the universe for a very good reason, because they all have something in common. And the thing they have in common is the reason why we can't study them properly. The reason is very simple. They're all changing. And those changes matter. Now I said we've been using telescopes for 400 years. But for most of that time, what we've tended to do is get a telescope, look at something, and say, okay, we understand that now, let's move on. And not come back to it. And so we're only looking at the static side of the universe. The aspects of the universe that are not changing. But these all matter, the changes here matter for all of these. Asteroids are moving, so you've got to be able to follow them to understand them. Supernova explosions, they're very dramatic. They're very rapidly evolving. We find extrasolar planets, again, because of the movement of the stars that they're going around. And again, and with the supermassive black holes, we find them because of the motion of stars, but we also know that they are themselves evolving, sometimes quite quickly. And so if we want to understand these, we have to understand the changes. And these changes get everywhere. This is our own sun. This is a sped-up movie of the sun, taken for a few years ago. It's one of my favourites. Taken by a satellite called SOHO. Now, this is an X-ray observation of the sun. So the gas here is incredibly hot. Millions of Kelvin, millions of degrees centigrade. Not the few thousand that the surface normally is, but much hotter. And you can see it changes. It evolves, it swirls. Occasionally you get flickers. And sometimes after one of those flickers, you'll get speckles all over the screen. My timing has got better. So you get the speckles all over the screen. And that's not X-rays, that's bits of the sun hitting the camera. So those speckles, those little flickers that you see, are explosions. Now they don't look very impressive, but to give you a sense of scale, you can probably see up at the top left there's a couple of little green splodges. They're bigger than the Earth. So these explosions are absolutely enormous. Vast amounts of energy coming out, throwing material out into space. And we don't really understand that. We know it's a lot to do with magnetic fields. We know the sun is a complicated magnetic field because it's swirling and twisting. And when you twist a magnetic field, it stores energy, a bit like an elastic band. But unlike an elastic band, that twisted magnetic field can snap, untwist, and then stick itself back together. And when it does that, it releases the energy. It's called magnetic reconnection. So we know that's where the energy is coming from. What we can't do is predict exactly when it was going to happen, or exactly how energetic it is. And that actually matters. Because those little speckles, they're tiny little subatomic particles, but they're electrically charged. And when the explosion happens on the side of the sun facing us, or at least close to facing us, they come and they fly past the Earth. So you're basically putting the entire Earth into a giant electric current. Now that has some good consequences. The northern lights are great. You get aurorae from these things. If you get a really big one of these solar flares pointing towards the Earth, you might be able to see the northern lights right the way to the equator. Certainly be able to see it around here. So there'd be some good sides. There'd be some less good sides. The national grid of Canada would blow up. This is a very serious problem if you're Canadian. Nobody else seems to mind very much. GPS would fail completely. Good 5% of all satellites would fall out of the sky. The internet would break. All of these things could happen with a really big one of these flares. Now we can't stop the flares happening, but if we can predict them, we can stop the damage. We can throw a trip switch on the national grid of Canada for a few minutes rather than blowing the whole thing up. We can boost the orbits of satellites for a while so that they don't fall out of the sky. We can do something about the GPS timing devices that the internet uses. We can protect ourselves from the damage if we can predict them. So understanding how the sun changes is incredibly important. But we've only really been studying it for 30 years in any detail. And even now, only very recently have we been able to look at the whole sun at once. We were always stuck with just looking at one side at a time. So there's still an awful lot we need to understand about this. And then there are surprise changes. This is another observation of the sun, but this isn't taken by a $100 million space satellite. This is taken by me, with a telescope about this size, in the docks, in Birkenhead, in the rain. Now there was a reason. And the reason was that little dot you just see above the centre and to the right. Now that looks like a sunspot, but it's not. Believe it or not, that little dot is Mercury. And a few years ago, a bit more than that now, there was a transit of Mercury. So Mercury crossed between us and the sun. And I thought it would be a really good idea to get a video of this. Now, this particular transit occurred at sunrise in summer. So I got up really early in the morning, got into the office, which was several miles away, and there were no trains, got the telescope out, set it up in the car park, got everything ready just as the sun was rising, and that's when the drizzle began. And it drizzled for the 6 hours of the transit, and then it stopped. I am never doing this again. 6 hours holding an umbrella over a telescope is not fun. But it was actually worth it, but not for the transit of Mercury. This is sacrilege, but the transit of Mercury is really dull. It's a dot, and over 6 hours it moves. I mean, who cares? But I got a secondary transit. I saw something else pass between me and the sun. And if you watch this bit of video really closely, you might just spot it. So watch closely and see if you can see this. There we go. Okay, there's not a huge amount of science in that, but I'm actually quite proud of it. One important thing about that is I could not have predicted that. It's a Ryanair flight. Perhaps more to the point, if I'd been 100 metres either way, I wouldn't have seen it. The angle would have been wrong. So I haven't got that video because I'm particularly clever. I've got that video because I was lucky and because I was looking. And that's often the case in astronomy. Some of the most exciting things are found almost but not quite by accident. They're often found because somebody is looking at something in a way that it's never been looked at before. So if we can find new ways of looking at the universe, not only will we answer some questions we already have, but we'll probably come up with some better questions. And that leads me to what we call dynamic astronomy, or time domain astrophysics. This is studying the changes in the universe, systematically, minute after minute, hour after hour, night after night, week after week, month after month, decade after decade, all of these changes. Now that's difficult to do, not fundamentally, but because of the way telescopes are designed to work. The majority of big professional telescopes around the world, you have to sit there and control. Somebody has to say, this is what the telescope is going to do now. So if I want to use one of these big telescopes, I've got to apply for time. Write an application, several pages of explanation about why the science I want to do, why I need to use this telescope, and so on. All of these go off to a committee of other astronomers, and they read all of these things and they rank them. And if you're lucky, you end up in the top 5% and you get your time. It's a really competitive process. But if you get your time, usually what you then do is you fly out to wherever the telescope is. So you end up spending a lot of time in places like Hawaii and the Canary Islands and Chile. It's an incredibly stressful job. You get there and you sit for your 2 or 3 or 4 nights at the telescope, you hope it stays clear, you gather your data, and then you bring it back and study it. And that's fine for a lot of astronomy, because what you're looking at is not changing. It will wait for you. But it's useless for these changing things. You can't study a supernova like that, because you might spend your 4 nights sitting at the telescope and none explode. Pointless. So we need a new way of running telescopes. And that's what robotic telescopes are. They're specifically designed to look at the changes in the universe. And this is the largest one in the world. It's called the Livable telescope. It's not in Liverpool. I have to stress this. A few years ago now, I was giving a talk at a school in Manchester. And I was asking kids, they were sort of 11, 12 years old, saying, why wouldn't you put a telescope in Liverpool? And they were saying, well, the weather's not very good, there's a lot of light pollution. One little kid put his hand up and said, if it was in Liverpool, somebody would nick it. This is the Palmer in the Canary Islands, and it's there because the skies are absolutely stunning. And why we built this thing, and we put it out there, because it's one of the best places in the world to put a telescope. Now, it's not a giant telescope. The mirror, the primary mirror, is 2 meters across, about yay big. And that's small by professional standards. The biggest telescopes have mirrors 10 meters across. But it's sophisticated. It's got a range of instruments, not just one camera, but 2 or 3 different cameras and a spectrograph and a polarimeter. Lots of different ways of measuring what's happening in the universe. But the most important thing is it's fast and it's flexible and it's automatic. And that's what makes it special. It's not the largest telescope in the world, but it's the largest robotic telescope in the world. And that's what means it can do science no other telescope can do. This is the observatory, the Observatory of the Roques los Muchachos, the Observatory of the Friendly Rocks, which is a great name. The Friendly Rocks are actually just to the left of me when I took this picture. And it's just a bunch of rocks, volcanic rocks, which look like they're having a chat. They really do. There's just a pile of them standing there. So they're the Friendly Rocks. But you can see the ridge of the mountain there is covered in telescopes. Now this is on the edge of an extinct, collapsed volcano. So you're on the ridge of this volcano. The active volcano, you may have heard about the news at the end of last year, is further south and further down the mountain. So up here there's no risk from that volcano. But at the top here, you're at the top of a very steep mountain that goes straight down to the sea. And that makes the air above the mountain very, very stable. Stars don't twinkle. You go out and they're just tiny, tiny, sharp little dots. Around here, stars twinkle all the time because of the turbulence in the atmosphere. They're nothing. And so we get incredibly sharp images. It's also not a very touristy island. It's probably the least touristy of all the big Canary Islands, because it doesn't have beaches. There are 2 beaches, one of which is artificial. So they really don't do the beach thing. So if they want to bring in foreign money, the best thing to do is have astronomy. Quite a large fraction of the economy of the island is based around astronomers. And that means they keep the skies incredibly dark. There are laws about light pollution which cover every action. And so the skies there are astonishing. You walk out in the middle of an observing room, and you look up once your eyes are adjusted to the dark, and you can't see constellations because there are too many stars. The Milky Way is not a sort of faint glowing band that you squint at. It's this huge bright thing spread out above you. It's absolutely beautiful. And because the skies are so good, we can do an awful lot of astronomy. And this particular telescope does it in a slightly different way to all the others. Instead of travelling out there, sitting on the telescope for a few nights and gathering data, what we do is we collect descriptions of what astronomers want the telescope to do. We call them observing programs. And these are collected by the Telescope Management Centre, which is an office in the building I'm in Liverpool. And these will describe the sequence of observations an astronomer wants to take. They might want to observe the same star every night for a year. Fine. They might want to observe that star every night for a year, but if it goes above a certain brightness, immediately start observing it every hour because it's doing something interesting. Or they might just say, wait till the supernova goes off and then observe it as quickly as possible. Once we've collected all those things, we send them out to the Palmer over the internet, and we go to bed. Or the pub, usually the pub. So nobody is operating this telescope. There's nobody on the Palmer doing anything, there's nobody in Liverpool doing anything, we're just letting it get on with it on its own. And the telescope has a computer system, a very sophisticated one, which looks through all the things it could be doing, and it looks at what's happening in the sky, and it gets information from other telescopes and other satellites, and from its own weather station. It brings all that together, and from minute to minute, second to second, it decides what is the best thing to do next. What will give us the best science? So it might be busy observing a star for somebody, and then a supernova goes off and it instantly interrupts what it's doing, moves across the sky and starts observing the supernova. And then when it's got that data, it goes back to the star. And it does all of this automatically. We then wake up the next day, download the results, and do the science. And so it's a very powerful way of studying how things in the universe are changing on timescales from minutes to years, in a way that no other telescope can really do. Now, because there's nothing else quite like this, lots of people want to play with this. I'm lucky. I work at John Moores University, so I get to play with it quite a lot. We own it, we run it, we get a fair bit of time. Astronomers in Spain get quite a lot of time on the telescope. La Palma is a Spanish island. If we give them time, we don't have to pay any rent. Works perfectly. But any astronomer in the world can apply for time on this telescope, and quite a lot do. And by the way, I do mean any astronomer, not any professional astronomer. If you have a good idea, you can apply for time. And if it is a good idea, it will get the time and then the observations will be taken. Most of the observing is done by professional astronomers because we have enough time to just sit there and write big applications. But we have had a number of amateurs around the UK and around the world with good ideas. They've got their observations and they've done the science themselves. So if you want to chat to me about that at the end, do feel free to come up and have a quick chat. If you've got any ideas for what this telescope might be able to do, talk to me. I might be able to help. But the other two things that are important is it doesn't just have to be doing work for research. 90% of the time the telescope is doing research, but 10% of the time it's doing education. This is what I got involved in the project 22 years ago now, crikey. While the telescope was being built in the factory we'd set up in the Birkenhead docks, it was decided that it was important that this was an educational resource as well as a research one. And so we set up a thing called the National Schools Observatory, and that means any school in the UK or Ireland, actually anywhere in the world, but particularly the UK and Ireland, can sign up completely free and get their own observations from the telescope. And we've got about 5,000 schools doing that every year now. It's not completely open-ended because it's quite a difficult thing to work out what to do. But you can observe galaxies, you can observe planets, you can observe stars, you can monitor asteroids as they move across the sky. So if anybody wants to come and chat to me about that afterwards, I run the project and I can tell you all about it. And we also get our students to use this because it's a professional telescope. And if they're going to learn what it's like to really be an astronomer, data from a research telescope is a very useful tool. If you want to know a little bit more about the way it works from schools, the basic idea is we've got a website which guides you, your pupils, your teachers, you, anybody, through the process of choosing what you want to observe. That gets sent to our Telescope Management Centre, which is that building there in Liverpool. They all go out to the telescope alongside the ones from the researchers. The telescope doesn't care who asked for it, just does it at the best possible time. Come back to us, download it into the school, and they do science. So this is as close as we can make it to what professional and research astronomers do, but removing some of the boring, tedious stuff like exposure time calculations, which are horrible, and air mass calculations and all these sorts of things. You don't want to have to do that. That's just painful. We do all of that. You get to make the decisions. We've recently opened this up so it's not just schools. So if you are keen on playing with the telescope, come along and sign up, feel free. Anybody can have a go. We restrict what people other than schools can do because we want to have the most time available for schools, but if you want to have a look, just come along to the website and sign up. And this is the kind of thing we can get. This is an observation I took for one of our distance learning students, actually, a guy called Bryn Davis, who was interested in star formation. So this is a cloud where stars are forming. And he wanted it because it's a nice picture, but he also wanted it because he wanted to understand some of the science. And there's a lot of science in this picture. The red colour is hydrogen. At the right temperature and pressure, hydrogen glows red. It has a particular emission line, 656 nanometers for those who want the details. So that reddish glow there is telling you there's a lot of hydrogen. You've also got the dark bits. Now that's dust. And when an astronomer talks about dust, he means anything that is made of molecules. So that's relatively cool. And dust blocks light. And so we can't see through it. And so we get this pattern there. But that tells us that there are complicated atoms there. It's not just hydrogen. There must be things like carbon there in order to create thick enough dust. And then you've got the bright bit in the middle, which is a brand new star. Now it's largely enclosed in this giant cloud, so we're not seeing it directly. But it must be incredibly hot because it's boiling away with hydrogen. You can see down the bottom left there, there's a kind of little hat-shaped thing. That's where the bubble of the hydrogen cloud is bursting. It's being broken through. And the only way you can do that is if there's ultraviolet light. And you only get ultraviolet light if stars are very hot. So in the centre there is a very big, very hot star. And we can tell all that by studying this picture. But it also looks nice. And I think that's actually quite important. A few years ago I was at an astronomy conference, the National Astronomy meeting. And I just went around everybody I could find, which is about 100 people, and say, what got you into astronomy? I was curious, I wanted to get some statistics. And there were lots of different reasons. Some it was a television programme, some had a telescope when they were little, but quite a lot, nearly half, said, well, I saw a picture of something and it looked really good and I wanted to know what it was and how it worked. And so we do spend time with this telescope taking nice pictures. Because they're nice, but because they also stimulate and inspire. So that's the way the telescope works. Before I go any further, does anybody have any questions about the way the telescope operates? Because if there's anything that's confusing you, now would be a good time to check before I move on. Everybody okay with how it operates and how it works? I'm seeing some nods, this is brilliant. Okay, so what I want to talk now is a little bit about some of the highlights that we've done with the telescope, the science highlights. And I'm just going to have a list up here, because it's done a lot of different things. But there is a theme behind all this. The first few there, I'm going to come back to a couple of those in a minute, but we've got novae. Now novae are relatively small stars that explode. And they tell us a lot about certain nuclear reactions. Supernovae, they're slightly larger stars that explode. Then we get black holes. That's what you get when a big star explodes. And then we get gamma ray bursts, which is enormous stars exploding. You will see a trend here. We do like things that explode. But all of these are telling us different kinds of physics. Gamma ray bursts have incredibly big, strong, complicated magnetic fields. But those magnetic fields are way beyond anything you'll ever get in the lab. One of my colleagues, Shiho Kobayashi, is an expert on magnetic fields that are rotating so that the edge of them is close to the speed of light. Now that's quite a niche field, but the physics there is awesome. And if you can get to grips with that, you will know a lot more about the nature of magnetism, not just anything else. So there's some important things that we can study from this. But at the same time, we're doing the stuff with the schools. Over 5,000 schools have got involved so far. We've taken nearly 200,000 observations for them. So all of this is happening on the same telescope, side by side, meshed together. Now I want to go through a couple of these in a bit more detail. And I'm going to start with near-Earth objects, because this is the field that I'm particularly interested in. Now, just in case this wasn't obvious, a near-Earth object is an object that gets near to the Earth. Astronomers are not good at naming things. Some of you may know that the largest telescope in the world is called the VLT, or the Very Large Telescope. That really is officially its name. You may not know that it's got a successor which is being built now, which is called the ELT, which really does stand for the Extremely Large Telescope. It's quite depressing. There was one that didn't actually get funded in the end, but it was going to be called OWL. And I thought that was a great name for a telescope until I discovered it stands for Overwhelmingly Large Telescope. Still, although it's not an imaginative name, it is descriptive. Now, this is not a photograph. Please do not panic. This is another one of these artist impressions. And this is the kind of thing that we think will happen if a large asteroid hits the Earth. Give you a sense of scale, that splash is about the same size as Europe. So it's big. And we think something like this, 50 million years ago, wiped out the dinosaurs. Apparently in spring. I don't know whether any of you saw the research recently, but they don't know exactly what year, but they do know this happened in spring. Paleontologists are brilliant. So something like this came down, smashed into the Earth, killed off the dinosaurs. Now, that was a shame, dinosaurs were cool, but selfishly, for us, that was a good thing. Because if this hadn't happened, we may not have been able to take over. And basically, I'll be talking to a hall full of lizards. It did happen, we took over, we run the world. Quite badly, but we run the world. If this happens again, we might be the ones to get wiped out, and then something else takes over. Maybe cockroaches. Cockroaches can survive everything. So unless you're a cockroach, this is now a bad thing. Okay? So we want to try and stop it happening. And to do that, we have to understand the asteroids. Now, we don't have to understand a lot of the details. It's enough to know that they're small, they're essentially rocky or sometimes metallic, and they orbit around the Sun. That's the main things we need to know. But what we do need to know is how they're moving. Now, this is the diagram you'll see in Wikipedia, textbooks, all that sort of thing, of the inner solar system. We've got the Sun in the centre. I've drawn on the orbits of Earth and Mars and Jupiter. Between Mars and Jupiter, there's this big fuzzy cloud that we call the asteroid belt. Now, this is a nice diagram because it's clean and it's simple and it's easy to understand. It's also wrong. This is where most of the asteroids are, but it's not where all of them are. This is where all of the known asteroids were a couple of years ago when I took this and made this diagram. And yes, there are lots in the asteroid belt. So many it just becomes a white blur. But you'll see there's some that are further out, sort of clumps of them there, following Jupiter around. They got pulled out of the asteroid belt by Jupiter's gravity. And they're in the same orbit as Jupiter now. But you've also got the ones in the middle. Now these have odd orbits. Quite a lot of them start in the asteroid belt, but they come in, go around the Sun, and go out again on oval, elliptical orbits. And every time they do that, they're crossing the orbit of the Earth. And if they happen to do that, when the Earth is in exactly the right place, then they will hit. Now, the Earth is a small target compared to the size of the solar system. So it's very unlikely, but it is possible. And these are the ones that we call near-Earth objects. These are the ones we're trying to find and track. And we do know they have hit. This is a big hole in Arizona called the Barringer Crater, or Meteor Crater. It's about, what's that? That's about a mile across, a couple hundred meters deep. And this was made by an asteroid about 50,000 years ago. Came down, 40 meters across, hit the Earth, moving at about 25 times the speed of sound, which is quite fast. Now, we think this was an iron asteroid. About 1 in 10 asteroids are made of iron rather than rock. And so when it hit the ground, 300,000 tons moving at 25 times the speed of sound, that's a huge amount of energy. Vast explosion, big hole in the ground. The asteroid itself is vaporized, but we can find remnants of it in the base. Now, that's a big hole, that's a big lump of metal moving very fast. But it's tiny for an asteroid. We can't find asteroids that small. All of those dots I showed you are 10, 100, even 1,000 times bigger than that. And we're not actually that worried about these things. They come down, they hit the Earth, they make a hole. Most of the time they hit places nobody cares about, oceans, deserts, Manchester, things like that. So we're not that concerned about these. What we're concerned with is the bigger ones, because when they hit the ground, it doesn't matter where they hit, the damage is much more extensive. They don't just make a bigger hole, they throw vast amounts of dust and soot and ash up into the atmosphere, where it spreads out and it blocks out the sunlight. And it gets very, very cold, very, very fast. We think a really big asteroid, sort of dinosaur killer size, could easily make it cold enough that the oceans freeze over completely, right away to the equator. And that's what will wipe us out. It's not the impact, it's the lack of food. And so we want to stop these things. We want to get them and push them out of the way before they get too close to us. And robotic telescopes are really good for this. Not so much for finding them. To find them, you need smaller, dedicated telescopes with really big cameras. But once you've found them, you need to track them, work out their orbits, and that's where robotic telescopes are perfect. And the process is actually quite simple. So imagine that a possible near-Earth object, one we might need to be slightly concerned about, but we're not sure, is detected by one of these smaller survey telescopes. Now, from those initial observations, you can estimate the orbit. It's not going to be very accurate, but it's a good start. And that means you can predict roughly where it's going to be for maybe a few nights. So as soon as possible, you automatically tell a telescope like the Livable telescope, and that will try and get some more detailed, high-precision observations as it moves across the sky. From that, you can then refine the orbit, once you've found it in the images, calculate the orbit more accurately, and often that's enough. You can then predict exactly where that asteroid is going to be for the next 100 years. If it's not, you go back and take a few more observations. But essentially, you keep going until you know whether it's going to hit us. And the vast majority of them it isn't, and you come back and check again in 50 years. Now, this is a nice process because it can be almost entirely automated. The survey telescopes can find these things roughly fairly accurately. The scheduling on a robotic telescope can happen automatically. The refinement of the orbit can happen automatically, but it turns out that one bit in the middle there, detecting the asteroid in the observations, is surprisingly difficult to get a computer to do well enough. You can write a computer program which finds all the asteroids, but it also finds lots of things that aren't. Or you can find you can write a computer program that only finds asteroids, but it misses any asteroids that are doing something a bit weird, moving too fast, moving in the wrong direction. And of course, they're the most interesting ones. And so, actually, the best way of doing this is the human eye. We can use the computers, and they can skim off all the easy ones, but there's going to be a few where we just want people to look at it to be absolutely certain. And I thought we'd have a quick go at that now, because it's always fun to hunting for asteroids. So this is an observation taken by the Livable telescope that contains an asteroid. Now, who thinks they can spot the asteroid? I will give you a clue, it's not the big white bright dot. Okay? Now, I've cheated a bit here. The cameras we put on these telescopes are very sensitive. Otherwise, there'd be no point having them there. And not only are they sensitive, they have a very big dynamic range. Now, those who haven't come across the dynamic range of a camera, it's essentially the number of different shades of grey that the camera can detect. The eyeball can detect 50 different shades of grey. Once had to explain that. The camera can detect 50,000 different shades of grey, which is obviously a lot more exciting, but it also means that if we want to look at what the camera's detected, we have to do some image processing. So what we do is we basically change the contrast. And you keep changing the contrast until it looks a bit like this. Now you can see that dot at the top there has got incredibly bright. That's a star. Ordinary star. Not a particularly bright one, but a moderately bright star. But you can now see that the sky has turned a kind of dull grey. When you've gone that far, you can see everything there is to see in this image. And so now you can definitely spot the asteroid. Can anybody see the asteroid? I've got a hand down. This is going to get complicated, because normally I'd give you a laser pointer, but it doesn't reach that far. Can you see my laser pointer?
Yeah. Up and now to the right.
The right?
All right, a little bit down. Right.
That one?
Well, yes, up.
That one?
Maybe.
Why do you think it's that one?
Because it looked darker than the other ones. I couldn't see anything darker.
Excellent. So it looks darker than the other one. It's a bit fainter. And asteroids are rocks, they're not particularly bright things like stars. Good. I'm going to ask you how confident you are. Now bear in mind that if you're wrong, we're all going to die.
ask someone else.
Okay, let's ask someone. Fair enough. Okay, I'm not going to pick on anybody else, but just out of curiosity, put your hand up if you think you know which one the asteroid is. 1, 2. Put your hand up if you've got absolutely no idea. Okay, fair enough. It's not easy, is it? Those of you who think you know what it is, remember which one you're looking at, which we're going to check in a second. Now, the problem, of course, is what you're looking at here is either asteroids or stars. And they both look like dots. Stars look like dots because they're really far away. Asteroids look like dots because they're basically just small. And so we're comparing dots with dots. That's not going to work. We need to be a bit cleverer. We need to think about the difference between stars and asteroids. And one of the differences, of course, is asteroids are moving and stars are not. Asteroids are orbiting the sun. The stars are further out into space. They might be drifting a little bit, but they're not going to move very much. So if we take another observation a couple of minutes later, and another one after that, and another one after that, and repeat them one after the other, the stars won't move, but the asteroid will. We call this blinking, and this is what you get. Now who can see the asteroid?
Yes.
Yeah. Quite a few hands going up. Right there, in the centre, little thing moving there, in a nice straight line. That's how you spot asteroids. It really is as simple as that. Now you might also notice a couple of other things. There's a little flash up here, and there's another one down here.
Yeah.
Yep, there. You also got a weird spike. That's just the star is too bright for the camera. Those two little flashes are not asteroids or stars. They're particles. They're cosmic rays, probably from the sun. They're tiny little charged particles, and they physically hit the camera. And that's why we take 3 or 4 observations, because if you just took 2, you might get 2 cosmic rays next to each other and think it was an asteroid. You're not going to get 4 in a row. And so, look at these observations, and if something moves in a nice straight line, you found an asteroid. And we've actually got people doing this, particularly schools. We take the observations, we put them on the website, and we let people get on with it, because, frankly, I don't have enough time, but other people do. So if you're interested yourself, that's the website, come along, and typically about once a week, we get a new alert for one we have to follow up, we take the observations, and we need you to look at it, find the asteroid and report its position back to us. And we can then go away and collate that with all the other observations and use it to work out the orbit. And we do this so that we can find out whether or not it's going to hit us. So far, none of them are, relax. But if we ever do need to know, at least we'll have plenty of warning. So that's one example. I wanted to give another quick one, which is another area of astronomy that people find fascinating, including me, exoplanets. Now, there are lots of different ways of finding extrasolar planets, but this is one of the most successful. It's called the transit method. This is another artist impression. This is what a star with an exoplanet might look like if you were really close to it. And you can see here, the planet is passing between us and the star. Fine. Now, you're not going to get a picture like this of a distant star because we can't see the star, it's just a tiny dot. But while that planet is there, some of the light of the star is not reaching you. And so the star will appear slightly fainter than it normally does. And then the planet goes out the other side and it goes back to normal brightness. And then the next orbit, the planet comes round and you get the little dip in brightness again. And this is called the transit method. And if you can measure the brightness of stars again and again and again and again, you find these little dips. And there are dedicated telescopes doing this. Particularly a satellite called Kepler got very, very good at this, found several thousand planets. But of course you can't look at all the stars. And so there's always room to try and look at some unusual stars to find unusual things. And that was done by a project called Trappist. Trappist was initially a telescope, but then it became a network of telescopes, including robotic ones like the Livable telescope. And one of their first systems of planets they ever found was called Trappist-1, and it's got 7 planets going around the same star, which is astonishing, and nearly all of those planets are essentially the same size as the Earth. When you read the press, they say 7 Earths found. They did not find 7 Earths. They found 7 things which are probably roughly the same size as the Earth-ish, which is as good as we can get. But they're certainly a lot smaller than Jupiter, and they're certainly a lot bigger than the Moon. So they're Earth-like, they're almost certainly rocky. And they were particularly exciting because quite a lot of them could have life on. We don't know that they do, but they're the right sort of planets. The diagram on the right here, I'll come to the one on the left in a second, but the diagram on the right here is a kind of plan view of this planetary system. And you can see the planets all orbiting around the star there. But you can also see 2 dashed lines. Now, if you're closest to the star than the inner dashed line, it's too hot to have water on the surface. And if, basically, it's above 100 degrees C. If you're further away than the outer dashed line, it's too cold, or the water will turn to ice. But between those two, the temperature could easily be exactly right to have some sort of liquid water on the surface. It's called the habitable zone or the Goldilocks zone, depending on who you talk to. And you can see 7 of the planets are inside that region. And some of the other ones are not far away from it. And so these are potentially planets that could have life on them. We don't know for certain that life requires water, but if it doesn't require water, it's probably so weird we wouldn't recognise it. So if we're going to look for life, we have to look for life that we think we would recognise, and water is an ingredient of that. Now the diagram on the left is the data that you use to find these planets. These are transit light curves. And you can see basically what happens here is you're measuring the brightness at the start, it goes along, and then it dips and comes back again. The length of the dip, so how long it lasts, tells you the speed of the orbit. So that tells us where the planet is. The depth of the dip tells you how big the planet is, because the bigger the planet, the more light it blocks out. So from those you can work out the orbit and size of all of these planets. It's a very good technique. Of course, that's not the real data. That's the data after it's been processed and carefully analysed. This is real data. And it's a lot messier. And it's messier because this system is really complicated. You can see here we don't have one dip. We have it drop in, and then it drops again, and then it goes up a bit further than it drops, and then it goes up again but not to the top. It's a mess. And that's because there's actually 3 different planets getting involved here. And the reason it's confusing is that first dip is 2 of the planets at the same time, just to be awkward. The first one then, a third planet then joins it, one of the planets leaves, another planet leaves, and then the third planet leaves. And so this is what the real data actually looks like. But you keep taking measurements, night after night, month after month, even year after year, and you can start to work out exactly what's going on. And the Livable telescope was heavily involved in this, because to do this properly, you've got to look 24 hours a day. If you have a gap, you might miss something like this. And Trappist was only one telescope. And so the Livable telescope was specifically used to fill in gaps when other telescopes couldn't do it. If they had a bad night in for example, Hawaii, this one could immediately take over as soon as the sun set on the partner. It was a really powerful system. And so we've been able to do some really exciting science with this telescope. We're answering some fundamental questions, mainly about explosions, but also about asteroids and planets, and so on. But we can't stop there. If you rest on your laurels in science, you get left behind very quickly. You've always got to be planning ahead. Now, this telescope has been operational for 15 years, which is a very long time for a professional telescope. It's still doing cutting-edge science. But in 10 years' time, it might not be. And so what we're doing is we're looking to the future, and we're trying to work out what do we need to do next to keep that cutting-edge science going. And there are various new kinds of science which we want to be able to support. We want to be able to help answer the questions. One of those is gravitational waves. This is a weird diagram of what happens when 2 very dense massive objects spiral into each other and crash. And they send ripples out through space-time. This is a diagram of those ripples. Those ripples are gravitational waves, and they go out into space, and if we can detect them, we can learn a lot about these systems. But they're not big. They look big in that diagram, but they're not big. A typical gravitational wave passing through this room would change your height slightly. And it would change your height by about 1/1000th of the size of an atom. That's quite hard to detect. But it's been done, which I still find astonishing. When I was doing my PhD, I did it in Glasgow, and in the basement of the building, I was on the top floor, but in the basement they were building some of these gravitational wave detection systems. And I was working late one night, and I popped the balloon and came back again. And somebody in the basement phoned up and said, "You just been a balloon, haven't you?" "Yes." "Can you not do that for 10 minutes? You're messing up our experiment with your footsteps." That's how sensitive these things are. And a few years ago, they got one. Before they'd actually finished building the system, they were just doing testing. And while they were doing the testing, at 2 different detectors, they saw a signal like this. So this is essentially the movement of 2 mirrors at the ends of a very, very long tunnel, essentially. And that movement is, in this particular case, is caused by ripples in space-time. Now, if you just saw one of these, it could be anything. But these things were about 100 or so miles apart, the 2 detectors, and you can see that the little wobbles are exactly the same. You can draw them on top of each other, and they're identical. That cannot happen by coincidence. That wouldn't happen by coincidence in the entire lifetime of the universe. So it's real, and it's caused by two massive black holes slamming into each other billions of light years away. And the ripples went through and they detected them. The first ever gravitational waves were found. And the astonishing thing was, not just that they found this, but the black holes were both weird. They were about 60 solar masses, 60 times the mass of the Sun. We had never found a black hole that size before, only small ones or much bigger ones. Now, the chances of the very first gravitational wave detection being two very weird black holes is not high. And so they're probably not very weird black holes, we just haven't found the techniques to find them. Now we do. And this is a diagram showing all of the really dense things that we know of in our galaxy, or at least in the local universe that are not supermassive black holes. Up the side there is mass. Basically, further up the more massive they get. The bottom hasn't got an axis, it's just to spread them out. All of the ones that are joined together by a line were detected by gravitational waves. And you can see the vast majority of really dense things that we know of in the universe were found by gravitational waves in the last 5 or 6 years. All the yellow ones at the bottom, they were found using ordinary telescopes. And you can see there's a big gap. And that's because we just didn't know this population of really weird black holes existed. Now we know there are thousands and thousands and thousands of them out there. It's changing our understanding of the nature of black holes. But it can't answer all the questions, because whenever one of these things goes, the gravitational waves are detected, that's it. That's all the gravitational wave detectors can do. They know it's happened, they can work out a little bit about the system. If we want to understand the physics, we then need a normal telescope to look at it. And there's a problem, because gravitational waves, you can detect them, but it's quite hard to work out where they came from. These are known as detection bananas, which I think is a great phrase. This is kind of a map of the sky, and the sort of banana-shaped things are where those gravitational waves probably came from. And you can see there's a challenge here, because they cover a large fraction of the sky, and you don't know where to point your telescope. However, there's some new gravitational wave detectors coming online soon, and they will make these things not bananas, but grapes. And they're starting to get small enough that we might be able to follow them up with robotic telescopes. So that's one bit of science we want to get to grips with. But the other one is what we call discovery telescopes. We've been doing time-domain astrophysics for about 20 years. The UK leads the world in this by quite a considerable margin. But other countries are beginning to catch up because they've realised how much fun it is, basically. And in particular, the Americans decided they wanted to do this. And in typical American style, they did this by throwing a very large amount of money at the problem. They're building something called the Rubin Observatory, or the Large Synoptic Survey Telescope. I think it's something like $30 billion. It's an enormous project. It will be operating properly next year, and that is the mirror. Before they make it shiny, but that's the mirror in this thing. 8 metres across and very thick. And it's very thick because it's very curved. And it's very curved because what they want to do is put one camera on this thing, not a whole suite of instruments, but one really big camera. Now, most of you have probably used a digital camera, probably have one in your mobile phone or something like that, and inside that digital camera is a chip, a CCD chip or something like that. And the typical chip inside a digital camera is smaller than my little fingernail. This is the chip inside the camera on the Rubin Observatory. It's enormous. It's actually not the chip stuck together, but it's huge. What the VRO will do is take incredibly deep pictures of most of the sky every night, again and again and again. And then there are massive computer systems which take all of those observations and find everything that changes. And then it flags up all the ones we don't know about. And they're expecting to find 1 million completely new variable objects every night for 10 years, which is amazing. The downside is they won't know what some of them are. A lot of them you can guess because they're recognisable. They're supernovae, they're variable stars, they're asteroids. But of that million, 1, 2, 10 will be completely weird. And there's nothing that the Rubin Observatory can do to follow them up. All it can do is take another picture the next night, but then it's too late. What we need is a robotic telescope that can follow it up, but our current one is not big enough or fast enough. So we'll build a new one. There's a code name, the NRT, which stands for New Robotic Telescope. I do hope we don't end up calling it that. But that's what it's currently called. It's going to be bigger. A 4-metre mirror, But most importantly, it's going to be faster. Currently, if something goes off in the universe and an alert is sent to the telescope, it takes it about 1.5 minutes to 2 minutes to get from there to where it wants to be and start observing. Now that's very fast for a big telescope, but we want to get that down to 20 seconds. That means very unusual design. We've got to use very lightweight materials, we've got to have a very unusual optical design to keep the telescope short. But we think we can do that. And the reason you want to get that down to 20 seconds is some of these things we think fade very fast. And then that extra minute that it takes the other telescope to get here, these objects could be 10 million times fainter. That's why the speed matters. Every second is a factor of 1,000 in brightness or something like that. So you've got to be really quick. Recently, we got the funding together to finish, not quite finish this, we've got about another couple of million to go. We're basically nearly there with this. We've now got all the engineers on board, we've got a collaboration with Spain to develop various parts of this thing, so this is now going to happen. And we're looking at first light in 4 or 5 years' time, just as the Vera Rubin Observatory is getting into its stride. So this thing will be following up detections by the Vera Rubin Observatory, it will be following up new gravitational wave detections, and it will be doing all the science we're currently doing as well. And we're going to be using it with schools. So there's the scope for even more exciting work with education. So it's going to be an exciting few years. The next 5, 10, 15, 20 years, you're going to be hearing a lot about this telescope. It's going to be making some really important and exciting discoveries. And it's all going to be happening here in the UK. We collaborate with anybody in the world who wants to get involved. But it's nice to know that here, we're able to lead this area of science simply by just thinking about it and getting in first and being open to collaboration, which is a really good way of working. So, I have talked a lot, I apologise, it's a long while since I've done this. I've tried to tell you a little bit about robotic telescopes and why I find them exciting. They're opening up a completely new way for us to look at the universe. We can see how it changes, systematically, seconds, minutes, hours, days, months, years. The Livable telescope leads the way in this, but we're not sitting on our laurels. We're going to be developing the new telescope. We're going to be going deeper, we're going to be going faster. And this is all great, but this really is just the beginning. So far, almost everything we've done with the telescope, we knew we were going to do before we even built it. But there are hints that there are things we didn't know were even there. If you like things like the Ryanair flight of the universe, the surprises. And that's what we're going to need the bigger telescope for to do as well. So the next 5, 10, 20 years, we're not just going to be answering the questions we've already got, but we're going to be coming up with newer, even more exciting questions. Basically, I have the best job in the world because it's my job to try and understand all this sort of stuff. So, thank you very much for listening.